It's fine. Why not just wait? Okay. So this is a room for professionals, so most of us know watershed restoration. I see it as a restoration of the geomorphology of a watershed. Stable watershed, sort of the definition, is that water and sediment are in balance. Somebody showed this slide. Connor showed this a good slide the other day. But really simplifying it, too much water, you have erosion. Too much sediment, you have aggradation. A stable watershed can handle the floods that watershed has without aggrading or degrading. Instability has been caused in almost all of our watersheds by human actions. There's a really good book about northern New Mexico called Enchantment and Exploitation. Turns out they used to go logging high in the mountains, and to get the logs down our streams, they would build huge dams, and they blow them up with dynamite. So we think of, sort of damage being done by overgrazing, as AT mentioned, roads, but actually historic logging blew up dams in all of our streams. And what I think is the restoration of the geomorphology restores this balance and allows a watershed to function properly. Next slide, please. And these are some of the functions of a healthy watershed. Again, it's pretty obvious. Healthy watershed will store water. It'll have a base flow to the stream. It mitigates flooding because the floodplain's accessible to the stream, and so water spreads out and slows down. Native species, and also a healthy watershed supports us by producing water, forage for wildlife and livestock. And so I think watershed restoration is an important thing, and I think I figured out how to prioritize it better. So next slide. So my experience, I learned a lot from, like we all do, from sort of extreme examples. So my first work was in the Rio Puerco watershed, and the Rio Puerco is one of the most eroded watersheds in the world. There's huge gullies. The Rio Puerco's dropped 100 feet. All the tributaries are head cutting upstream. And so they're like, oh, you're a new restorationist. How do you fix this 20-foot deep, foot wide gully? And I'd be like, there's no way to do that. So I came up with an unofficial motto, which was, don't throw your money in a hole. And so whether clients that I meet are, they're land managers or they're private clients, generally people take you to the worst piece of their property and say, I need restoration. That's what's wrong. And yet we all know watershed restoration is to start from the top down. We know it's a holistic thing. And so that's why I titled my talk this way. We all tend to basically, we find projects that are close to the road, that are visible, that, somebody's a squeaky wheel, and then we write a grant for that, and we end up working on the site that we wrote the grant for, not really looking at the big picture. So then even if you do get a project where you get to assess an entire watershed, I've spent literally weeks walking watersheds, walking up every little stream, GPSing thousands of points. I've assessed the entire Rio Dosto. That was 1,200 points. And really, it was a blast. It was great fun, but it was very time consuming. And then you have to kind of prioritize within that, go back to your data, write down a lot of notes. It takes several weeks to really assess even a small watershed in a good form. So the steps of what I'm doing is basically creating a watershed model in ArcGIS using 3D Analyst and Spatial Analyst, creating flow lines, looking at those, identifying head cuts through a slope analysis tool, basically just through an analysis of slopes, and finding the areas that actually are at the top of gullies and are moving up valley and draining more of the watershed, and then actually identifying unique locations in the landscape for a treatment we call the plug-and-pond treatment. It's also known as the Rosgen Priority 1 treatment. Lastly, actually pretty neat, we just put it in Excel and prioritize. So look at benefits versus cost, and we decide what we want to do. Next, please. This is, I knew this would be hard to see on the big screen, but basically there's little red flow lines and there's blue flow lines. This is analysis I did at Canyon de Chelly National Monument. This is taking LiDAR data, and it's a pretty simple process. I have the model on my poster outside, but basically break the landscape up into 1 meter cells and look at flow direction from those cells, and basically ArcGIS for us decides basically where water's going to flow, and it models where all the streams show up. And so these flow lines start at what we consider 2,000 cells or 2,000 square meters. You can do this at any scale, and this is the same thing the USGS does to draw streams on a map, but we can take that into very fine scales with ArcGIS. And right here, I've just done a Strahler stream order to it. So there's a lot of parameters we can come up with. Next, please. Secondly, this is another area. This is a farm. This is a dryland farm I looked at. Now, it's hard to see, but we basically broke the stream into 1 meter segments and then looked for areas of high slope. And this particular area, we thought basically over 20-degree slope of a 1 meter segment identified as red, and so there's some red here, there's a little bit of a head cutting there. And so I think we can look at channels and find head cuts more effectively, again, than by walking for weeks on end. And then actually you can prioritize head cuts by how close they are to the top of the watershed. If they're almost to the top of a watershed, we'll give up. Or if they're really deep, again, you can measure depth in ArcGIS as well. It's probably too much work for what you're going to get out of it. But a small head cut that's cutting through a beautiful valley is probably worth fixing. So I think there's prioritization to do for that. And a head cut, again, this is basically a waterfall in a stream. If you notice the dead vegetation down here, the water table's dropped, and live, healthy riparian vegetation upstream. And these move up valley and drain our wetlands and streams. Next, please. These are some head cut treatments. There's probably 5 or 6 we use, sort of we being Bill Z. Dyke's kind of crew. This is a rock rundown. We do this on sort of, this is a valley, sort of a, this is not a very tough structure, but this is built by hands by students in a day. We basically widen the head cut a whole bunch. We lay it back, we tamp it, we seed it with native seeds. And actually head cuts are one of the wettest places on the landscape because all the water in this meadow is expressed at this face. And so by covering it with rock, we really reduce evaporation. And grass will come out literally in a month in a good summer monsoon. So this will be held together with grass. When you have a channel, we actually try to mimic a waterfall. We call this a Zuni bowl because Bill got it from the Zuni. And this is basically a step pool. Water pours over the lip. A key thing about this is water hits water and loses its forward momentum and sort of loses its, all those force vectors going downstream and kind of comes up in a glide. And this is how streams disperse energy. Steep streams have waterfalls because that is the only stable energetic form for that steep stream. And so we can build these structures by hand. We can build them with machines. But basically, we can fix head cuts. Next. And what I was looking at, I started doing this flow line modeling, and there's different patterns that we found that actually show you where you can build these plug and pond structures. And I'm kind of going to show this, and I'll show you what I'm talking about with the structure. Basically, parallel channels are a good place for further investigation. A plug and pond is an area where we take a gully and we build a plug in it, and we put the water back in a former channel or back on a former wetland. And so when you have parallel channels, you're like, wait, streams don't, there's usually not 2 streams in the same valley. What's going on there? One of them is usually a gully, and the other is usually the former stream. And so there's unique locations on the landscape where we can do a day or 2 of work and create acres and acres of wetland. And it's really been really powerful tool for us. This is the Valles Caldera National Preserve. I'm doing a lot of restoration work up there with the Los Amigos de Valles Caldera. And basically, the only thing we do now for our restoration projects, we tried a lot of different techniques. The only things we do are fix head cuts and build plug and ponds. This is what it's just the most effective things we've really found that we can do. And a really important thing is plug and ponds don't work in a lot of situations where the gully's up the middle of the valley. So we just had a lot of intense degradation and the whole watershed's been lost. Well, then you have a new base elevation and you do induced meandering, you do something else with that. So a lot of situations this doesn't work, but in about half of them it will, and it's actually fixes the gully completely. Thank you, Shannon. This is a picture of it right here. This is a big wetland. We had a gully downstream. We built a plug right there, and essentially diverted the water back onto the wetland at a higher elevation, about 3 feet up. Some of the benefits, we're restoring to a historic channel. We restore the water table, so the water comes back up and the wetland vegetation grows back in. Increase wetland area, we retain runoff. And one thing I'm testing is I think we can attenuate snowmelt later in the year. Lately in the Valles Caldera and the Jemez Mountains, snowmelt comes out in March. I mean, this is a lot faster than it used to come out. This particular site flows till June now. And so I've used thermographs, and I'm setting up a study with controls before and after to look at if we can actually just see the thermograph wet later in the year. A stable thermograph just shows it's underwater, essentially. So I think this is a really powerful tool in our tributaries, where if we don't want to work in the mainstream, we should be installing these in these tributaries. And almost every tributary we've seen is gullied through some, probably through sheep. Next, please. This is a construction. These also have been called groundwater dams. We stole this from Dave Rosgen on one and a guy named Thomas Biebighauser on the other. So other people have developed these techniques. We come in, we strip off the sod. So this is, we've picked up a lot of Juncus balticus sod, and we're storing it. We go and we dig a hole, and we dig to wetland clay. And so we build a clay core dam. We've stored our topsoil to the side. We put topsoil on top of the dam and put the rest in the bottom of the pond. And then we cover it with the sod. And the flowers will still be hanging there. I mean, they'll still be like, healthy. They won't die. They won't even really know what happened to them. It happened so fast. Next, please. This is one of our first project sites. This is a gullied stream. That's a pipeline, did a lot of gulling. But this is an old wagon road that takes the water out of this wetland, takes it right into the river. We built a plug here and a plug there. And so this is aerial photo. This was 2 days of work. There's a 1/4 mile of wetland created in 2 days of work. It's all about the location. And I think we can see the location with LiDAR. That's kind of the whole gist. And I can go home now. Next. This is another project site. These are all dams. This is what it looks like. We're basically holding water in a wetland, wetting the entire area. We're fixing the gullies and lifting the water table all the way down. So the last step is sort of simple and it's obvious, but we take all of the benefits. So imagine, we can kind of look and imagine how much wetland we'll gain, how much wetland we'll protect, and we value them by cost in Excel, and you basically just prioritize that way. So we can look at entire watersheds, figure out what things we should fix. And I'm not saying it's not worth planting native vegetation or fixing streams or doing some of that work, but these two techniques are kind of the very first two I'd start with. And we prioritize this, and we prioritize based on restoration goals, and then we kind of break it down, and that's what we do. Next, please. A unique situation I think this would work is in post-fire restoration. So if you imagine a post-fire flood, the first things that are going to come undone are all your headcuts are going to start moving upstream rapidly. And in the Vice caldera, this is a sort of a huge flood. The floods were huge. I mean, 20-year flood and a ½ inch rainstorm. All these little valleys have areas of like steep little streams, kind of intermittent stream, with a little wetland, say a 1/4 acre wetland, and most of those wetlands are gullied through. So I think you can come in, and we're going to come into an area called Rito de los Indios the next few years, come into these little wetlands and build plug-in ponds in them to capture this material. And a big problem with the wetland restoration that we've been struggling with for years is how do you fill them in? Wetlands are low sediment, thank you. And where do you find the material to fill the wetland in with? And one, with the plug-in pond, you fill the wetland in with water. But then if you have a fire upstream, I'm suggesting this material is the material we have for the next 100 years that can rebuild wetlands in a natural fashion. And in the Vice caldera, a lot of our hill slopes are pretty fried. But most of the wetlands, just through overbank flooding, look really good. So the natural gullies, the trails the cows created, were just covered by ash. I mean, this stuff, I'm picking it up here. You can literally lift it. You stick your hand, it just comes up. That's biochar. That is free fertilizer, free soil. And if it's being parked in wetlands, we can go in there and try to modify the wetland and store it in ponds and basically do a lot of restoration for free. And so I would suggest after fires coming in right away and looking for these really quick places, and maybe you build 20, maybe it doesn't take much. You get it and you catch that first post-fire flood. And then to take it one step further, in this particular landscape, you could plug the entire San Antonio Creek. And we could have plugged the creek and saved the fish and sent the water out over a 1,000-acre wetland. There's a lot of big valles, we call them, big wetlands up there. So that's a big thing. We need a lot of permissions from everybody to do that. But I mean, you could do this at any scale. There's a lot of work. If you're more interested in plug-in pond on the Feather River in California, there's some really good science going on from Stanford, Berkeley, and other places up there. So this has been done on huge river scales. I'm talking about doing it on small scale, but it works at any scale. Okay, next. Next steps, give me a call. Let's talk about it sometime. I'd love to answer any of your questions. So thank you very much.
When we were talking yesterday, I don't understand some of the terminology, but you said, did I understand you correctly that you said that in the California and Washington and Oregon that this data is already available and you just need to distill it, but here you've got to collect the data?
Very true. AT had to bring up the weak point. I love you for it. It's really important to say this, and I think you all may get this. LiDAR is not available for everywhere yet. I've tried to get ahead of the game because it will be available soon. In the Vice caldera, we actually have 2 separate seasons. It's a critical zone observatory. It's sort of a geophysics place. But many states, the San Luis Valley, there's a lot of places there's LiDAR existing for everything. There's also different levels of data, such as photogrammetry, which is a 6-inch contour you can do with a drone pretty quickly and also get really good photos. So you can work with different levels of data, LiDAR just being the best. But that's a really good question.
So I'm really interested in these kinds of structures, but the one thing that I constantly thinking about when thinking about installing them into an area is thinking about, okay, so historic um, water flow in the area and how we need to build these structures so that they still work now, but will hold up to the extreme rainstorms that we get, with the change in precipitation patterns, and you get these huge gully washers that I've seen cases where everything is working, and then all of a sudden you get two back-to-back 10-year, 100-year events, and they just wash out. So how do you deal with that of building something that works now, but that hopefully won't be washed out in the next year or two?
Well, you're getting to the reason I don't really work in streams that much anymore. There's always that risk with a restoration project in a channel. With the plug-in pond, I don't know if I really emphasize this, we're taking it out of a gully and putting it in a former channel, and then it's just a matter of giving it enough freeboard. And once it's in a former channel, it generally returns back to this, back to the gully downstream in a nice fashion, and so it really can't break. I know that's kind of excessive to say, but they don't break easily. And the wetland vegetation is very strong, and we're working in small watersheds. So if we were to work in a big river, I would be worried about that. So it's a really good point.
That was a great presentation, Steve.
Thank you.
Have you had an opportunity to apply any of your techniques on projects that involve dam removal, low head dam removal?
I have not, actually. It sounds really interesting.
Do you think that the techniques that you've been working on would be good in anticipation of setting them up prior to the dam removal?
I think a lot of things I skipped were just all the data you can get from the flow line stuff. I mean, I have the ability to click on a flow line anywhere and calculate the watershed area. So I think, as we all know, LiDAR is just helping all of us do so much more.
I was referring more to the Zuni bowls and
the
other sorts of construction techniques you've been doing for years.
I think so. Low head dams, I imagine you're just going to end up with a huge delta at the top of the dam that has to cut through.
Right.
So yes, but again, you can have floods too big that would just tear them out. But if I had to, try to hold those deltas in place, that's how I would do it. So I don't know if I'd succeed because I've never done it.
Right.
All right. Thanks.
Thanks.
This is going to sound like a huge question, but where and what do you monitor to understand how you've, succeeded here?
We do a lot of vegetation monitoring. We do geomorphology, which is kind of elevation monitoring, cross sections and longitudinal profile. I do photo points. I have thermographs in above and below these structures to sort of, before and after I build them, to see if I'm lengthening stream flow. There's obviously some cost to building a small dam that holds water in it, but hopefully the benefit of increased wetland area and increased base flow is going to make up for that. But that is a good question. And any other ideas you have, I'd love to talk about. So, thank you.
Thank you, Steve. That was great.